Hello, AP Physics C students. We're going to go through problem 16. So really you should try to do as much of it on your own as possible, maybe all of part A, and then come back to the video to see how I'm doing it. Or if you're still unsure how to do it, maybe try part A, part 1, then come see how I do it, and maybe go piecemeal like that. Okay, so first thing we do is we look at our diagram here, and we look at the description of the objects here. We got a charged insulating sphere, radius little a, and it's inside this shell, uncharged conducting sphere, inner radius b, outer radius capital R. It tells us the inner sphere is charged negative q, and R is our coordinate over which we're going to be integrating, over which we're going to be considering the different distances from the center. All right, so we're broken into different regions. First one is R is less than A, so we know we're using Gauss's law, one, because it's got a spherical symmetry, even though we're looking in a circular cross-section, but also because it says to use Gauss's law. So we write Gauss's law, integral of E dot dA equals the charge enclosed over epsilon naught. And just in case you're still having a little bit of trouble seeing how I draw epsilon on the board, it's this, right? Sort of like a C with a horizontal line across. Although if you still want to draw it as the squiggly, like the cursive capital E, it's okay, but this is, I think, the better way to do it. And then whenever we do Gauss's law, we draw a Gaussian surface. Now, we're doing 4 different regions of this picture. So if you don't want to draw all the Gaussian surfaces, you just want to sort of imagine them in your head, that's fine. I'm going to be drawing them on the screen because I have the luxury of getting rid of them. But it might mess up your picture and make it very cluttered if you keep drawing all the Gaussian surfaces. So if you can imagine them in your head, maybe that's a better way of doing it. It's totally up to you what's going to work for you. All right, so here's our Gaussian surface. We draw our Gaussian sphere, which again in cross-section is going to be a circle, so that its radius is less than a, the radius of the inner sphere. And then it's so important we identify what sort of object we're looking at. And here it says it's an insulating sphere. So we know that the charge is going to be distributed all throughout. Now, it doesn't actually say it's of a uniform charge density. If it doesn't say so, let's assume it is. And so we are going to play our usual game of figuring out how much charge is enclosed as a ratio of the total charge in the sphere. So if it's a constant or uniform charge density, rho, that means that Q over V is going to equal Q over V. Now, here I'm writing capital negative Q because that's the total charge on the sphere over the whole volume of that sphere, and little q is going to play the role of whatever charge is enclosed by our Gaussian surface. And I call that volume V prime. That's the volume of our little mini sphere. You have to remind yourselves the equation for volume of a sphere, that's 4/3 pi r cubed. For the left-hand one, that's the entire volume of that whole sphere, which is a radius a, so I replace r with a. And remember, little r, that is the coordinate we're going to be using to indicate the distance from center, so that's the radius of our Gaussian surface. Clearly, we see the 4/3 and the pi go away, so we're going to solve this for lowercase q. And so it's going to be negative q, little r cubed over a cubed, and this is going to play the role of whatever charge is enclosed, the ratio of the charge of the inner sphere. Okay, so now we're going to sum over dA, which hopefully at this point you're starting to get the idea of really just finding the surface area of our Gaussian surface. And since it's a sphere, we remind ourselves that the surface area of a sphere is 4 pi r squared. Remember, it's little r, because that's the radius of the Gaussian surface. And then replace q enclosed with this bit here, but don't forget about the epsilon naught. So we should have this. Now we're just going to solve this for E. We notice already 2 factors of r go away. And if you haven't done it yet, just go ahead and solve it for E on your own. There are many different ways to express this. Some students like to pull the 1/4 pi epsilon naught out to the outside, because that's sort of like the constant that goes along with Gauss's law. Other students like to put it all together as one big fraction, if that makes more sense to you. And still other students say, well, 1/4 pi epsilon naught, that's k, and they like to write fewer symbols, so they can write it as k, negative k capital Q r over a cubed. Any one of these is absolutely fine. You don't have to write all 3 of them. Just, pick whichever one makes the most sense to you. All right, let's go to our second region. R is between A and B. So again, we're going to write Gauss's law, and we draw our Gaussian surface. Here's A, here's B. So here's our Gaussian surface. It's going to be in the hollow region between the inner sphere and the outer shell. Again, all we're looking for is to see what charge is enclosed there. Well, the great thing is we're enclosing the entire inner sphere. You may say to yourself, well, what about the outer sphere? Well, 1, the outer sphere is uncharged, but 2, it's not part of the Gaussian surface, right? All we care about is the charge enclosed by our Gaussian surface. We don't care what's happening outside. That's not how Gauss's law works, right? Gauss's law is only concerned with whatever charge is enclosed by our Gaussian surface, and we're enclosing the entire charge here, so there's really nothing to do. There's no integration to do. We know what's going to happen. It's basically the inner sphere is acting as a point charge. And so we can fast forward directly to our answer. It's just going to be negative q over 4 pi epsilon naught r squared, or just negative k q over r squared, right? It's literally the same thing as a point charge. You don't even have to do the whole thing. Now, if you want to go through the whole Gauss's law and sum up the bits of area to find 4 pi r squared, you could do that, but we've already sort of done this before. There's no real reason to. So like I said, we always want to work smarter, not harder, sort of fast forward to the results we already know. And if we're enclosing the entire charge, it acts like a point charge. Let's go on to regions 3 and 4. Now, why am I putting 3 and 4 on the same slide here, and why is there such little space between 3 and 4? Well, let's take a look. Region 3 is R between B and R. So let's draw our Gaussian surface. It's there, right? It's in the conductor. And this is why it's so important to recognize what sort of material we're looking at. Well, we don't even have to do Gauss's law. If you're looking at the Gaussian surface drawn inside the conductor, we know our answer. Done deal, E equals 0. That's it. That's it. You hope and pray for someone to ask you for the field inside the conductor, because don't even do Gauss's law. It's going to be 0 no matter what. But as we talked about in class the other day, what are the implications of this? Well, if the field within this Gaussian surface has to be 0, that's implying the net charge is 0 inside that Gaussian surface. So what are the implications of this? Well, what's included inside our Gaussian surface? Well, we have the inner sphere, which we know has a net charge of negative q, but we have to have 0 net charge inside our Gaussian surface. So if this has negative q, there has to also be positive q somewhere. Well, where is it? It's got to be on the inner surface of the conducting sphere. Why the inner surface? Well, this goes back to electrostatic equilibrium. We know that any sort of excess charge always collects on the surface, right? So that means that it's going to sort of push electrons away from that inner surface, leaving behind positive charge. How much positive charge? It's got to be positive capital Q. So that inside our dashed line, we have negative Q from the inner sphere, positive Q from this surface. Don't care about anything else, because we only care about what's inside the Gaussian surface, but these two have to sum to 0, so that the net field is 0. What is the other implication? Well, I said that we have this positive charge on the inner surface of the conducting sphere, because what's really happening is that electrons are moving, right? Positive charges aren't drawn towards the inner. What's actually happening is electrons inside the conductor feel the presence of the inside sphere, which is negatively charged. They get repelled to the outside, leaving behind positive charge. So the outer surface of the conducting shell attains the negative charge. How much? Well, it's got to be negative Q, right? Because if a charge of positive Q accumulates on the inner surface and the whole sphere is uncharged, if there's a positive Q on the inner surface, there better be negative Q on the outer surface. All right, let's go into region 4 here, where R is greater than capital R. And we write Gauss's law, and we draw our Gaussian surface, where again, if you don't want to keep drawing all the Gaussian surfaces, if you just want to imagine them, that's great, but I have the luxury of erasing those older Gaussian surfaces and putting in the newer one, and so this one's going to be outside the entire system. But again, let's play the game of working smarter, not harder. We're now enclosing everything. So let's tally up all the charges we're enclosing. Working from the inside out, we have a negative Q here. For the inner surface, we have positive Q, and the outer surface, we have negative Q. What's the total charge enclosed? It's just going to be negative Q. And so let's not do the whole Gauss's law business of adding up the bits of area. We know what's going to happen. This is acting the exact same thing as a point charge of negative Q. And so let's just fast forward to the end. Right? We don't have to go through the whole thing. Now, again, if you want to go through the whole thing and prove it yourself, that's fine, but let's look for these patterns. That if we're enclosing that entire charge, don't worry about it. Just think about the total charge. All right, so here's our summary of all the different fields and all the different regions, because now we're going to go on to letter B, sketching out the graph. Okay, so at this point, definitely pause the video and sketch out what you think the graph looks like, and then come back to see how I do it. Okay, so first I'm going to put some little dashed lines there. Notice that I've included only this region down here because it says positives away from the center, negatives towards the center, and all these fields are negative except for in region 3 here, right? So I know I'm going to be in the negative E section, which of course I heavily imply by putting more space below the R axis than above. All right, so let's take it one at a time. Going from the inside out, when R is less than A, we have this, and what shape is this going to be? Well, K is a constant, Q is a constant, A is a constant, right? A is just the radius of that inner sphere. R is the coordinate that changes, and this is a linear function. R is 0, E is 0, and it's just going to start 0, 0. It's going to be linear with a negative slope. Then we get into region 2 between A and B, and here we have our usual inverse square dependence, so it's going to look something like this. And then region 3, real simple, it's going to be 0, so it just drops right down to 0 there. And then region 4, we again have that exact same inverse square dependence. Now, just like we talked about in class, this sort of picks up. So imagine, and in fact, it might actually help you to draw this entire shape and then just sort of erase this bit in between. So you have one continuous curve here, and then just get rid of this and then drop it over to 0. But that's what's really happening, right? Because, of course, R, big R, is a bigger distance than B is, and so it should pick up from there. Now, it doesn't say to do so, but it might be a good idea for us to label some pertinent points on the e-axis. So for example, this point here, just take a second and think through what's the value of e at this point so we can label it on the e-axis. So this is the point where r is equal to a. So we look at this function, which describes the electric field between those 2 points, and we put r as a in here. Well, one factor of a is going to cancel with one factor of a there, and so we're going to get negative kq over a squared, which when you think about it, it just makes sense, right? We're right at the surface here. We're at distance a from the center. This is basically acting like a point charge once we're outside of it. So this is just kq over r squared, where r just happens to be a. By that same token, what's the field going to be at letter B? Well, at letter B, we're basically here just looking at the field from this point charge, which, I mean, it's not a point charge, but it's acting like one, right? And so it's just going to be negative kq over b squared, where we just look at this right here and just put b in for r. And what about over here? Well, we just put capital R in for little r, so that's going to be negative kq over capital R squared.